Hello. In this part of the video, we're going to go through Chapter 2, Syntax Analysis. We're going to go through how to take this Grammar 2.4 and put it through LL1 parsing and SLR parsing. Uh, we're going to do the simple example, but if you want a more complicated example, I will link to the textbook's website, which has a solutions manual, and you can do some of the exercises there to practice the method here. I chose to do a simple activity, at least a textbook example, that way that I could finish this video much faster. But if you find yourself wanting help, feel free to ask in the comments section and I'll hopefully get to it or somebody else can get to you. And yeah, if you find the video helpful in any way or you want more, you can click the likes button, subscribe as well if it helps. And yeah, without further ado, let's get started. So we're gonna go through LL1 pausing and SLR, which are very simple, but just as a quick little recap, because I feel like it will explain. Um, on chapter 2 is that we have to understand what is pausing. So pausing, if you've done your theoretical computer science or finite automata, you'll know that you're just taking a string and you want to know if a particular string follows a certain language or syntax. And that syntax is defined by the context-free grammar. And if we're able to generate a tree you for the string using the grammar, like so, then the string over here follows the grammar. It's syntactically correct. But if we cannot generate a tree like so, then it is not syntactically correct, meaning that it does not follow the language that the context-free grammar is defined for. And if you've done this activity before, you know that if you're trying to generate a tree, you would apply some sort of method such as guessing or whatnot. But how would we do that programmatically? Uh, Here, you'd have your parsing algorithm, which would be your LL1 and your SLR and your GLR and many others. And what these will do is that they will generate some sort of table or some sort of index that it will use to generate the tree or some sort of way to generate the tree. And each algorithm is different, but not all algorithms work for all grammar. So for example, if you want to make an LL1, if you want to make use of the LL1 algorithm, first you have to make sure that your grammar is not ambiguous. And what does being ambiguous mean? It means that for the same string over here, we're able to generate two separate trees, that is for two separate syntax trees. And this is proof that the language is ambiguous. And this example is also from the textbook as well. And yeah, you try to, so you'd have to change this grammar. If you want to make use of the LL1 algorithm, you'd have to remove the ambiguity from this algorithm over here. And I will link to a video in the in the description um, on how to remove the ambiguity. But the video is by Anita R. It's a very wonderful creator. These for compiler-based lesson. And second thing, if you want to work with the LL1 algorithm, is to make sure that there's no left recursion. And here's an example of left recursion here. It's where when you're generating a syntax tree, it has the capability of generating or skewing to the left side. So as you can see over here, my control panel is not on. Let me just turn this on. As you can see, is that I forgot to put a production rule T to indicate the start. So you can see that it can recursively grow using the one production onto the left side. So you would not, the LL1 algorithm would not work if this was the case. Rather, it works if it's skewed to the right instead, but not on the left side. So you'd want to remove this as well. And here's the video by Anita R. I'll also link it in the description. She explains what is left recursion and how to remove it as well. And also, third, for if you want to use the L1 algorithm, is remove left factor, or is to apply left factoring where applicable. And this is for conditions where you have multiple production rules, let's say production rule T, and they have production rules that start with the same terminals or non-terminals. So you would have to remove this such that there's only one production rule. At least each production rule starts off with a unique terminal or non-terminal. So for this case, you would have to either add a new rule to get rid of these over here. And in the video, she does explain how to do that. Elimination of left recursion. I think I got the videos mixed up. Yes, that I did. So I will link the videos in the description. So now let's actually get started. Let's see. So if you want to do Ella, we'll start off with LL1 pausing. This one already has the ambiguity removed from at least the example over here. That was just for demonstrating the example. This is the grammar 2.4 without the ambiguity. And I think it's does not need left factoring. So here are the steps you do. Given a grammar, here are the steps you'd follow in order to generate LL1 pause table. So step one, eliminate ambiguity. So I don't think this is not ambiguous at all. Eliminate left recursion. There is each production rule, at least from all the production rule for T, each one starts off with unique, and each production rule for R, each one starts off with unique. So it's good. It does not have a left recursion. And perform left factorization where required. Same thing as well. There's no okay, left recursion. This does not have the T. I mean, it does not. Sorry about that. Left factorization. This does not need any left factorization because they do not start with the same. Each production rule for each non-terminal does not start off with the same set of tokens or a set of non-terminals of tokens. And two, number four, add an extra start production. S prime produces S dollar sign. So the dollar sign signifies the end of the file or end of line or end of the file character. So that means you have to add a new rule to this. And that rule would be, let's see, let me just copy this in case I need it later. So this is for L1. Okay, so we add a new rule T prime, and this produces, where did it go? This produces T dollar sign. The reason we chose T is because it's the start symbol. Usually the first production rule is the start rule, but do double check which one is the start rule so that you can have this. And now secondly, calculate the first for every production and the follow for every non-terminal. So we have to calculate the nullable first and follow sets over here. And there are rules that you have to follow when you have to generate these sets over here. But what I like to do, at least to help me remember, is there's a way to see what is nullable and what is first and what is follow visually speaking. So to give you an idea, so let's say we have the production rule T. So we want to tell if this is nullable or not. And what does nullable mean? It means that the non-terminal can disappear, or it has a transition rule. Let's say T produces epsilon, or it produces rules such that it can disappear. So in this case, is there a way for us to get T to produce an epsilon, like with no other children over here? And there is. So we start off with T, and this produces R as well. And R can produce nothing, and this cannot. Nothing also means epsilon as well. So like so. So this over here is how you can tell if like a rule is nullable, because you can produce nothing. So that's how you can tell nullability. What about first? So the way first works is that you have a non-terminal, and you want to know what are the set of terminals that would appear first. What would be the first set of terminals? Uh, in this case, could be um, could be A, that could be T. This one is a good example. So T could produce A, which produces T, and then produces C. Mind the handwriting. So this is an A, not a Q. Let me see. Let me erase that then. So let me just rewrite it. So notice that A is the first character that appears over here. And you can also produce another terminal, which is T. Let me just put this down over here. So T can produce R, and R can produce B and R. And again, notice that B is the first terminal to appear from T over here. So it's B and A essentially, and I don't think there's any other rule. And so that's how you get like your first and follow program at least like visually. Uh, not to do the follow, I mean. So the follow is quite simple. So you would have your production rule, your non-terminal here, and it would produce whatever it needs to produce. And we want to know what are the characters or what are the terminals that would appear after this rule. Let's say that it was let's say, how do we get t? Let's say you have t prime over here. T prime produces this, and then t prime produces that. And notice that right after t, so after it's done producing what it needs to produce here, like it doesn't matter what the depth of this is, right after this t, we're followed by this terminal over here, this dollar sign. And that's how and the set of characters that appear after it, or the first set of characters that appear after it is the what the follow set will contain. So we would have let's see, just an eraser. So we would have this. We have t. No, I just want something. Let's just say x, and x would produce some sort of rule over here. So usually t, you'd notice that, let's see, yeah, after t, there would be some sort of character that appears over here, and that's usually the follow, at least that the follow, and it could also be in situations like this as well, where you have x, y, and then z, and then z would produce a. So the follow of t would be whatever. So the first character, the first non-terminal or terminal that appears after t is it's gonna be this a over here, because once this is done producing whatever it needs to do, this it goes back up, it goes to z, and then z produces this, and that means this. So that's what the follow set is. That's the visual way. There is like there are rules you can follow to do that, and I can link to again Anita's videos to do that. So that is how you at least can like understand how the nullable, first, and follow work essentially. And I thought I thought this would explain how that is. So that is how I understand these sets over here. So let's get started producing this. So we're gonna have let's see. So we have to generate the nullable set first. So the first thing to these to doing LL1 is to calculate the first for every production rule and the follow. It does not mention the nullable, but it is useful to have the nullable set. And so we get the nullable set for each terminal. So we're gonna get it for n prime. So this is the we'll get to this later. We'll get to this later. I'll just put it down. Ah, okay, there's disobeying commands. There we go. So we'll get to that later. Now we're gonna generate the look ahead sets, these sets for each production, each for each non-terminal non-terminal. So let's start off with T prime. So T prime, to get the nullable, we just put in for each production rule for T prime. And we check the nullability of that. So let me expand this to go as wide as it can. So I have T prime T dollar sign over here. And this can expand to, so since it's just, so this would be for each production rule, and it only has one production rule, so we're just gonna put that production rule over here. And then this can expand to this. And I believe this is an and concatenation and nullable dollar sign, I believe. I'd have to double check this. Let me double check to make sure that I'm on the right path. Uh, okay, let me. Nullable, nullable. Okay, here we are. So I'm just gonna copy this. Thought I put it down here. There we go. I think that's everything. All right, hello again. So I got the algorithms for formally defining the nullable and first set. I could not find the follow set for some reason, but this is good enough for now. Let's see. So yeah, we're on the right path. We're just saying nullable t is this. So we're just gonna put this on its own line. So at least make it easier to read. And so we just have to calculate the nullable t and nullable of the dollar sign. So we'll get to those later. So now let's do t. So this would be nullable for each production rule of t, nullable of r, or, so as you can imagine, this is the union, yeah. I think, yeah, you'd use v to represent the or, and so you can type this or nullable ATC over here. And this would break down to nullable of R or nullable of A and nullable of A of T and nullable of C. So that would be, so we just have to solve for each one and we'll have a rule. I feel like, oh yeah, I forgot to put in the other rule here. So it's gonna be R. Here we just have to find R and the production rules of R. Oh, again, same issue as before. I don't have the epsilon transition. Let's see, epsilon character copy. There you go. Stop and present. All right, I got my epsilon character, so it's gonna be nullable of this, or nullable of nullable of BR. And the reason we're using or for each production is because just one of them has to be true in order for the non-terminal to be like characterized uh, as a nullable. non-terminal, meaning that it can disappear. So we only need one production rule for it to disappear. And this one is an and because I think it accounts for like all the rules or everything that makes it up has to be nullable for it to disappear. And if one of them cannot disappear, then that would make it not nullable. If that makes sense. Let's see. So now let's start with this. So is this nullable? That's a yes. So it's a true, or is this nullable? So it's the same thing, but it doesn't really matter if we break it apart like into, let me just put this here, nullable this, or nullable B and R, and nullable R. Okay, because this part is true, we don't have to care about this part at all. So we can just disregard it. But even so, this would say, is this nullable? Since this is a terminal um, cannot be nullable because it is a terminal. It's a character. And so this would be true. At least this would be false, I mean. And nullable of R is what we're trying to find out. And I believe that we assume everything to be false at first. So it's going to be like this, I believe, assuming that I forgot what's the best way to handle this. There's an example in the textbook that explains it, but I usually just ignore this bit if it's like from the same set. So I just assume it's a false. This could be wrong. All right. I don't think I'll add an. I don't have enough time to add a mental note. But either way, whatever this is, the final answer here will just be true. And now that we have true, we're going to have nullable R, we know is true. Or since we already have one true, the rest of this doesn't really matter, but we'll do it just cause. So this over here, this nullable rule, since it's a terminal, A is a terminal, and lowercase a is a terminal, it's going to be false because it's a terminal. And this, again, we assume it's a false. Again, I'd have to reread the textbook just to get that right. And this right here, we assume is a false. And again, you'd have to double check how to properly handle the these non-terminals here. But the textbook does talk about assuming that everything is false. But whatever results you get, you know that this will be true because of this, at least this part of here. Then you make your way up, nullable T. So this is an and because this is the only one, so it's just going to be an and. So nullable T, you know that nullable T is true because we just calculated here, and nullable dollar sign. The dollar sign is a terminal, so it cannot be true. So the final answer here will be false. So this over here is not true. It's not nullable because of that. And that is how you get that. Some things to note is how to properly handle the rules. I just assume it's false and just go from there. But it is, I'll try to see if I can find the section and just make a video edit afterwards. Right, now that we've done with that, you have to find the first of each row. And to find the first, here's the algorithm that you can use. So we have to find the first for each non-terminal. For me, I'm just gonna say t prime. So we're gonna have to find the first of this, and then the first of that, and then lastly the first of R. So just gonna change this. Okay, now that we found that, what do we do from here? To find the first of t prime, we have to find the first of each production rule. So it's going to be t prime, and then it's going to be union everything else. Or at least all the other production rule. Everything else is every other production rule. And since there's only just the one, it's just this. And we can break it apart into first of t union first of the first of dollar sign over here. Again, I'm following this rule, and before I also followed this rule when working again this algorithm. So we found the first of this. So now we have to find the first of t. And to do that, let's see, how does this work? We find the first of R, the first production rule of T, R, union, the first production rule of ATC. And then from here, it's just going to be the first of R, union. So since it's first of ATC, it's actually, we can reduce it to just first of A because of this production rule over here. Since this is not nullable, we can reduce this to just that because that's the first character. It cannot be any other character as well. So we can just leave it like that and solve for first of R. And let's see, first of R. First of R is gonna be this, an epsilon and the first of BR. So the first of epsilon, since it's nullable, epsilon is nullable, we're going to it's going to just be an empty set since nothing comes afterwards. Union first of B. Since there's no other production rules, we can, I think this is like the bottom, so we can just go even further and actually solve it. So we're gonna have that, and then we're gonna have this over here. And now that is the first of R. And now we're gonna do the first of T. The first of T, remember we said it's this to that, and the first of R we just did, it's B. Union first of A, since A is a terminal, it's gonna be that. And the final answer here is just gonna be AB, just to order them here. And now we do the same over here, where the first of T prime is that. We're just gonna calculate, we already calculated the first of T, so it's gonna be A, B, union dollar sign, leaving us with the final answer of A, B, dollar sign. So, and that is how we get the first set. And now we're going to do the follow set as well. I could not find the algorithm for the follow set, so please go through the textbook if there is one. I do remember there being one, but my memory is not that good at the moment. So, so I'm just gonna go through it using intuition, at least the same visual technique, because the concept still matches. For me, it works better to see it visually, and hopefully for you too. But if it doesn't, you can go through and find the rule that defines how to do the follow set over here, or the algorithm that defines the follow set. And the first step is so our goal is to find the follow set from the follow set of each non-terminal. So we'll start off T prime, and then just copy this for this. There you go. Not too many. There you go. And now we're gonna have TR, and then we're gonna have just T. And then this over here, and this over there. So how does this work? So it's the same idea. What would be the first character that would appear, at least a set of characters that would appear after we've produced T prime? So in this case, the best way to do it here is to look where T prime shows up on the right-hand side, and then that will help us know which characters would come first. So we find out where T prime shows up on the right-hand side of the production rules, and the non-terminal or terminal that shows up there, we just get the first of it, and that should work. And at the moment, there isn't none. Let me just turn this on. So at the moment, there isn't none. So we're just going to, so it's just going to be an empty set at the moment. So now we're going to do the follow of t. So we're going to see where t shows up on the right hand side, and you'll notice that it shows up on the uh, shows up here. So what comes after t is this over here, and that's the only, yeah, and also here. So t also shows up here, and what comes after it is the dollar sign. So since these are two terminals that would come after it, we can just say the dollar sign, and first let's start with C and then dollar sign. You can write the dollar sign first. I just like to put the dollar sign last in the set, but the order doesn't really matter. You know? So this equal to first of the dollar sign union first of the C character. So it's right over here. So the first character that comes here is this, and the first that comes after that is that. And hence we get this over here. Now we're going to get the follow of R. And how does this work? The follow of R, where does R appear? R appears over here, and R appears over here. So we're going to go through each case. So since R appears for production rule T, there's nothing that comes after here. There's like no rule that comes after here. Like, so in this case, whatever follows R will follow T. That is because if you think about it, so we have the rule R over here, and whatever R produces, RT will go back over here, and then T will produce these, like this will go up, and this will go up to X, and then X will produce some sort of rule. So since R is here, and the first character that shows up is here, so the follow of T will be the same as the follow of R over here, because the first character that comes after these is this one over here. So in this case, we're gonna say, because of this reasoning, we can say the follow of R equals to the follow of T. So hopefully that makes sense. I'm pretty sure there is in the algorithm. I'll try to look for an algorithm if I can find one. I'll just put it on the screen to help. So yeah, that's the first rule. That's how follow of T works, if that makes sense. You could try to wrap your head around it. You can rewatch the video just to get it again. And then T of R over here is also R appears here. Uh, since R is produced by R, it becomes the idea whatever follows R is this. By the same logic, it's gonna be this follow of R. But if it's usually in these situations, I don't include the follow of R because follow of R equals to the follow of R. And a union is a wrong character to use. It's actually supposed to be the subset of character. This one over here, the pen. So the right character to use is this one over here, the subset of as well. So we can just write, so you can just remove this part over here. Not really needed, really. Yeah, and now that we've done this, our final answer will be C $sign. If this does not make sense how we got here, watch the video again or find the proper algorithm that explains it. I'm going off the visual method over here. So, okay, dokie. Now that we've done this, we found our nullable set, our first set, and our follower set over here. And now that we've done this, what comes next is simple. Okay, I don't think we got anything wrong here. So what comes next is to generate a look-ahead set. And a look-ahead set is how we know which production rule to choose next. Let me get my eraser over here. So here's a formula that you can use to generate your look-ahead set, which will also help us to get our pause table as well. And will also help us see if there are any conflicts with our LL1 pauser. You see. So to generate a look ahead set, it's just simple. So you're gonna have there you go. See, I put it this. So to generate a look-ahead set, so for each production rule, we're gonna say first of alpha, union follow of X if alpha is nullable. Alpha refers to the whole production rule. But if it's not nullable, then we just say first of that. And that is how we generate our nullable set. And who do we generate our nullable? It is our look ahead set for each production rule. So this is going to be, let's just copy this. We're going to have 5 of these. Doop, doop, and doop. Okay, cool. So in this case, we're going to start off with T prime, which produces T dollar sign. Then we have TR, it's going to produce R. We're just going to have T over here. It's going to produce A, T, and C. And then we're going to have R, which produces epsilon. So I can just leave it empty for now, but I think I'll just copy this since we already have the character. No, I'm just going to do this, make things easy. And we're going to have R produces BR. Awesome. Okay. Let's see. So now we have to generate the first set. So the first of this entire rule over here, since we already did it up over here, we did this rule. We know that it's not nullable. So this entire rule. So if we were to do the first to check if it's nullable, it is not nullable because of this sign over here. So that means we just have to find the first of T dollar sign, which would give us what would it give us? Let's see. It's gonna be the first of T union the first of dollar sign. Okay, so this will just be what's the first of T? We already calculated that. The first of T is AB. So that means the first of this one's going to be AB dollar sign. All right, now that we've done this, I think that's the look ahead set for that. Now we're going to do the look ahead set for the second rule, which is this. So R, we already know that R over here is nullable. Or this whole production rule is nullable because we did it over here. This whole production rule is nullable R. So we already know that R is nullable. So that means we're going to have to find the first of R union the follow of T, which gives us, what does it give us? The follow of T, okay, the first of R is going to be B, I believe. There you go. It's going to be B. Union the follow of T, which is this over here. It's going to be C dollar sign. There you go. And now we're going to do this. Let's finish up this. You can tell sort of drifting away here. There you go. On that. And that is the lookout set for that production rule. And now we're going to do the production rule for T produces ATC. So would you check, is this rule nullable or not? It is not nullable because it starts off with a terminal. So that means it's just going to be the first of ATC, which produces first of A, which we can reduce to first of A, which gives us A. That's very simple. And now we do this. Is epsilon nullable? Is this production rule nullable? Yes, it is because it's epsilon. So it's going to be first of this whole production rule, which is just epsilon union first follow of R. So we know that first of epsilon is just going to be an empty set, which is the fall of R. It's just going to be this as the C character and that dollar sign. And finish it off, it's just going to be C dollar sign. Perfect. Now we're going to do this. Is this production rule nullable? At least this one. Yes. No, it's not, because it starts off with a terminal. So it's going to be first of BR, which we can reduce to first of B, which we get as B. So now we've found the look-ahead sets for each rule. Now that we've done this, we have to check if there's a conflict. So a conflict is when you try to generate a table, or we would try to generate the table for L1, you would end up with a conflict where you want to predict what the next rule is, but you can't decide because there are two rules, the two production rules that take up the same spot or would both be possible. So each one would have to be unique. So to check for that, for each production rule, for each non-terminal, you check their production rules, and you have to make sure that the look-ahead sets are not overlapping. And that's pretty much it. So for example, since T prime, like the non-terminal T prime only has one rule, there's obviously no overlap between the look-ahead sets for its production rules. T has two production rules, and they don't overlap. So the values here do not overlap with the values here. If they did, then there would be a conflict, meaning that the grammar the grammar is not suitable for LL1 parsing and would have to be changed further. And the reason there would be a conflict is, as stated before, it's either ambiguous, or there's left factoring, or there's the left recursion. And then you have look ahead for non-terminal R. It has two production rules. They do not overlap, and so they are valid. So none of the production rules, everything is valid. Now none of them overlap. And now that we have this, we can build our pause table, at least our LL1 pause table. And you would do that like this. So I'm just gonna put this over here. We're gonna start off with the first rule over here, T prime. So this is how this is how we generate the LL1 pause table. So you're gonna have a table where on the each row, at least on the row header, you're gonna have each non-terminal, and on the columns, you're gonna have each terminal. You're gonna have each terminal, and you're going to put in the rules over here. So for this production rule, you'll put it in a column that says A, B, and dollar sign. So for T prime, so this row over here, we're going to add T prime produces T dollar sign on these columns over here. So to do that, it's you just do it. So I'm just gonna put this over here. So I'm just gonna copy this. So this goes over here because A, and this goes over here because of B over here, and this goes over here, dollar sign. So that's the first rule. Got it. Now we're gonna do this rule. So for T, meaning that we're dealing with this row over here, T, we're gonna add T produces R onto B, C, and dollar sign. I'm just gonna copy this. Okay, where do we put it? So B and C and dollar sign over here. And now we're going to do A. This one, we're gonna do this production rule. So we're going to add it into A over here. So like this. And yeah, that is how you add. So an example of a conflict would be if you're adding a production rule and two rules just end up in the same spot. This is a conflict of here. But since we haven't done that, there is no conflict. So that's what an example of a conflict would look like. Okay. I'm just all right. So now we're gonna produce for R produces epsilon. We're going to add it on C and dollar sign. So for this row over here, we're gonna add this row over here and this row over here. Cool. And then we're going to add, just gonna copy this. So we're gonna add this row in column B. And that is it. Now that is all the production rule. We've done each and every single one of them. I'm just gonna erase this. So now that you have your table over here, now that you have your table, there was no conflict, you can now use it to start pausing. And the algorithm that you can use to pause it is this one over here, where you would have the following. You'd have the following instructions, and what you would do is that you would just follow the algorithm, and it would help you. So you would give yourself, let's say, you would give yourself the following production rule, be over here. You'd give yourself the following string, and you would use the following table, and you would just apply the algorithm to generate, at least use this algorithm to generate the the the, the syntax tree. And that is how you produce a pause table as well. And you can also write a pause table programmatically as well. Let me paste the example. And okay, so I'll just put this over here. Programmatic example. It's not how you spell programmatic. Okay, it's good. So a programmatic example of the table. So a pause table is one way of representing the tree. Another way is doing this if A, B, or dollar sign, then match this. So you can write it. These do the exact same thing. Give me a pen. So these do the exact same thing. So you can write it like this or this. So this is just programmatic and this is that, and they follow the same. So if you're gonna pause using the table, this is how you would do it. And this over here does the exact same thing, but programmatically, if you were to write it yourself. And yeah, that is how you do LL1. Pause table, relatively simple. You just generate the look ahead sets, and once you do that, you've practically achieved it. And do go over how to deal with conflicts as well. And the conflicts usually means that you have to change the grammar as well. And now the conflicts usually happen mostly in LL1, so because of the grammar. But yeah, let's move on to SLR, which is a pausing algorithm that can handle a lot more than the LL1 algorithm because it does not require you to change the grammar as much um, as LN1 would. Okay, let's see. So what's the first thing? Let me just change this. What my controls here? Okay, these keep disappearing on me. Okay, so here are the steps to generating a. So we're also going to do the same thing where we generate a pause table, but using the SLR algorithm. And the SLR algorithm relies on a DFA at its core. So we're going to convert this grammar over here into an NFA, and from an NFA to a DFA using the same method we discussed in a previous tutorial on, uh, I believe it was for lexical analysis. So yeah, let's, without further ado, uh, step one, add production rule S prime. Uh, produce S, where S is the start of this grammar. as the start symbol of the grammar. So in this case, T is our start symbol. So we're just going to say add T prime produces T. So the difference, another thing I forgot to mention is that with SLR, the pausing is from the top to the bottom compared to LL1's bottom to the top. No, I think I got that. So SLR is the bottom up algorithm, while LL1 is the top down because it starts off from the top and then it tries to predict what the next row will be and then it goes down. SLR starts off from the bottom and it makes its way up over here. So yeah, so that's the first step, which T prime produces that. And what else? Make an NFA for the right-hand side of each production. So for each production rule, we have to make an NFA, and we use the same idea as before in lexical analysis, where we take each rule and we you may turn each one into a fragment. So I'm just gonna put the T over here. We generate a fragment for each production rule. So I'm just gonna put this here. Yeah, there we go. Oh, just need a bit more space, a bit more room. So, see. Okay, cool. So we have epsilon over here. I'm just gonna paste it over here. I think we just take epsilon, borrow it from here. There you go. And then you just put it over here. And just take this, you just only need to resize it. That's not good. Okay, so put that back. Screw it. Gonna do this. Okay, it's gone. So I'm just gonna put this over here. So I'm just gonna evenly space out each character. Please stop doing that. Okay, this is definitely part of the video I need to fast forward. Okay, just create a bit of space between each rule. All right. So now that we're here, what do we do? So we just take each production rule and we turn it into a fragment. And the transitions that we're gonna use is that each non-terminal and terminal on the right-hand side will be a transition value. So we're just gonna put T over here. You can leave it blank for now. Then we're gonna put in another production rule. So it starts off with this root production rule over here, and then we're just gonna change it to this. This is a bit too big, so we're just gonna lower it to that. So yeah, we're just gonna start off, since there's only one rule, there's gonna be one transition. There's only one non-terminal, there's only one character, which is a non-terminal. And so we're just gonna put in the character T. Then we're gonna raise, yeah. But yeah, that's it. And since this is the last rule, at least the last state, in this fragment, we're gonna turn it into an except state. We're gonna use the same format as before, where we just gonna change to make it use the dashes instead to signify that this is an except state. And now we move this over here. There's only one rule, so we just move it here. Then we move it, and then we write R. Okay. And then since it's the last one, it's going to be substate. So now we're going to do the same thing over here, but this time we have 3 transitions. We have A, T, C. That's going to be like so. Okay. Gonna need a bit more space here. And the seam. Okay, we're gonna do this. Gonna do that. Cool. So yeah, this is gonna transition to here, and here it's gonna be A, small lead, So small letter A, big letter T, and big letter C. And since this one is the last one, we're gonna make it into dashes, like so. All right, hopefully you're with me. We're gonna put this over here. Since this is an epsilon, there's technically nothing here. We can just leave it like so. And since it's the last state in this fragment, it's just going to be our final state, our accept state. Now I'm gonna copy this over here. And then since there are two transitions, we're gonna have this. There you go. So that's aligned. So this is gonna transition to this, transition to that. And so it's just gonna be small letter B and big letter R. And yeah, so that is what we do. And this one, we turn it into an accept state. So now that we've done this, what we're going to do next is we're going to name our transitions over here. So you can use numbers, but in the textbook they use letters. So we're just gonna plop in some letters over here. So this is gonna be A, it's gonna be B, C, D, E, F, G, H, I, J, K. I'm just gonna lower this. Again, load it a bit too much. There you go. J, K, and then L. Okay. So now that we've done this, another thing that we have to do is now that we've named our states, we're gonna have to number each. We're gonna have to number each production, each final accept state after their respective production rule. So this production rule here, we're just gonna call it production rule. Stop. Production rule. We're just gonna call it production rule 0. No, stop it. Wow. Okay. It's gonna be production rule 0. Please don't do this to me. We're just gonna say 0 here, and this is gonna be production rule 1. Okay, I did the same mistake. It's gonna be 1. Okay, this works. Okay, production rule 0 and production rule 1. This will be production rule 2. And this will be production rule 3. And this will be production rule 4. Okay, let me just change the colors just to distinguish them as much as we can so that we don't confuse them. So we're just gonna put in blue. Hopefully that's a good color choice. And this is gonna be blue and blue and blue. And bingo. Now that we have our production rules here, what we do is that we're gonna mark this one for 0, and this one for 1, and this one for 2, respective to this, and this one for 3, respective to 4. And this will be useful later. And now that we've done this, the next thing, just do this. So the next thing we can do is that we have to connect each and every one of them using an epsilon transition. So we turn these fragments into one giant NFA. And to accomplish that, we have to go through each production rule in each state that has a non-terminal transition. Also, by the way, each transition corresponds to an action that will be relevant later on. So for each state that is a non-terminal, at least that transitions, for each state that has a non-terminal transition coming out of it, we're going to go to its respective production rules. So, for example, T over here, So we have the example T and T. Since T is coming out of here, we're gonna make a transition from here and also here. And let's change it to be like so, and to be like so. And we're gonna make these into epsilon transition. And let's give it ourselves a bit more space. And these rows over here, we're just gonna come on. Okay, I cannot move them as easily. Okay, there you go. Cool. Pretty cool upside. So we're gonna add an epsilon transition here. So now we have a R coming out of here. So since it's coming out of C, we're going to move this C to point to this one because that's a production, at least the segment for R. And then we're gonna connect this with this one over here, which is a segment for this as well. Yeah, and that is that. That is R. Okay, I see what's happening here. No, I won't say something. I'm gonna put this over there. Is it okay? It could be. I think I might have messed that up. There you go. Remove this. Cool. What do we have here? God, there's so much happening. So I'm just gonna move these two where. All right, all right, all right. So this produces that, and R also goes to this over here. Same idea. So I'm just gonna give this a bit more space over here. So yeah, this is not my favorite thing to do. As you can see, it's quickly getting messy. But yeah, hopefully you can stick along. So F over here has a production rule T coming out of it. So that means we're gonna take it to itself over here. Just do it from here. Make it loopy. And this is a null transition. And then it also goes to the one above as well, which is this over here. I'm just gonna move it here. And make it into this transition. Now we're going to move, I think that is done, yeah. Then we're gonna do this over here, which will take us to this row. We're gonna make it loopy. We make a transition like so. And gonna transition like that. And that is how you get, I think that is the complete one. And to make it more complete, we're going to add the extra character. So to signify the start state, we're gonna put that in. So that is our for connected NFA with the start state and this state over here. And yeah, let's see. If the NFA state S has an outgoing transition on non-terminal N, add epsilon transitions to S to the starting states of NFAs for the right-hand side of the N, which is what we just did. And then now it says convert the combined NFA to a DFA. Use the starting state of the NFA for the production added in step 1 as the start state. As the start state, cool. All right. So convert the combined NFA to DFA. Use the start state of the NFA for the production added in step 1 as the starting state for the combined NFA. So now we have to convert. All right. So let's get started on converting this NFA into a DFA using the method we learned in lexical analysis. So the first step is to start off with the start state over here in the NFA states. We can name our DFA into 1. And now we have to find the e-closure of this whole thing over here. So just a quick recap on how e-closure works is you practically ask yourself, from your current state, where can you go? Which other state can you go to by doing nothing? And nothing in this case is the epsilon transition. So by following the epsilon transitions, where can we go? So when we open up our pen tool, the pen tool over here, let me just have the creation tools clipped just in case. Here we go. When we start off with A over here, never mind, this was a mistake. So we're gonna have A. So A is the first part of the epsilon transition, which takes us to E over here. So we're gonna have E as our next state. And then we're gonna follow this epsilon transition, which takes us to C. And now we have ACE. And now this will take us to this I over here. And this does not going anywhere. And this will also take us to J. And J does not have any epsilon transitions coming out. So the first E closure takes us all the way to there. So our first E closure will consist of these set of elements. So I'm just going to write them down over here. So it's going to be A, C, E, I, J. There you go. So now we ask ourselves, from this set of elements, or at least from this set of states, where can we go with these transition values over here? And notice that the green are for the non-terminal, for the terminal transitions, and the gray are for the non-terminal condition transitions. So with A, let's see, with the small letter A, where can we go? Let's see. We can go from, let's change the color of this pen to red. So we can go from E, we can go between take this route, which will take us to F. What else? Yeah, nothing else really. So that means we're gonna have to add a new route over here. So it's called this, which is just going to consist of the state F. We're gonna name this 2. So this will tell us its transitions to state 2. And yeah. So I'm just gonna get the eraser. So now ask ourselves the same question. Where can we transition from this set of states over here using B? The first one I see is J, taking us to K. And where else? This does not, this does not, this does not, does not. Okay. So we just have a second transition that takes us to K. So we're just going to put in K over here. And we're going to put in 3. And then we're just going to say this takes us to 3. And do we have the same for EC? I don't think so. So J does not have a C. This does not. This does not. This does not. And this does not. And yeah. So now we go here. Now we have to look at their transitions for T and R. So for this, we have B. So we have T, which takes us to B. To C does not have a T transition. E does not. I does not, and J does not. Yeah, it does not. So in this case, it's just B. So what we do is we have B as its own. So we're gonna name it 4, and this will just be 4. And yeah, that's how this works. And now for R, do you have a transition for R? Let's see. So yeah, we have this one over here, C, which takes us to D. And yeah, that's it. It's just D. So it's gonna say D over here. This is gonna be 5. Hopefully that does not. What's that sound? Okay. So it's just gonna take us to 5. And we have no other transitions over here. And so we carry on. So here, just erase this, and this. So now let's ask ourselves, now that we have F, we have to do the epsilon transition for the epsilon closure for F. So where will that take us? So we start off F, and F will take us back to E, which will just be this, and F will take us to C, just this, and then C will take us to J, is this, and will also take us to I, is this. So it's just C, E, F, J, I. Let's double check. This goes nowhere. This has no epsilon closure. This already took us there, and this already took us to the ones at the bottom. So I think that is the second group. So now when we do finalize the set, it's going to be C, right, C, E, F, I, J. Okay, cool. So that's the final grouping. And now we ask ourselves, which transitions does it have for A? So here it's going to be E takes us to F. Yeah, it's E taking us to F. And what else? C, nope. E, the F, no. I, J, J does not have it. So it's just taking us to F. And we already have the production rule for F. So just have to say 2 over here. So it takes us to itself. Now, what do we have? So for B, what do we have for B? Pen. So what do we have for B? B takes us to K over here. And okay, so this B takes us to, so from J we can go to K using B. C does not have that, does not have a B. All right, so it's just K. So we already have a transition for that as well. So this is going to be 3, since this is that. All right. What else do we have here? So for the pen tool, where can we go using the transition for T? So from F, we can go to G. So this one over here. And yeah, we have nothing else. All right, so it just takes us to G. So we're just going to create a new row for G. We're gonna name this 6. And that means from here, we have a transition for 6. Yeah, and eraser, pen tool. And then now we want for R. R takes us here to D. And yeah, that's the only transition for D. So it just takes us to D, which we already have over here. And we're just going to type in 5. There you go. And now let's go to here. So those are the rules. Gonna erase this and that. Nice. Now we just have to K. Where does K take us? So K. So now to do an epsilon transition. K. And how did we get K? Oh yeah, you have the J. So we have K over here. So E closure for K starts off with this. Then it takes us to this. So it's JK. And yeah, I think it's just these two. So yeah, it's just gonna be these two and none other. So we're just going to add the J and K. So now we ask ourselves the questions. There's no transition for A, but there's one for B. So it's gonna take us to K, which is itself. then there's no other transitions for anything else. And this will take us, so for R, it's just going to take us to L. So we're just going to name this L, and this is going to be 7. Okay, 7. This will take us to 7. Perfect. Yeah, I think that is J. There's not much else to say. So I'm just gonna erase. Doop, doop. We don't need the highlighter. We just need a regular pen. Now we do B. So B takes us nowhere. So it does not have any transitions, so we can just leave it blank. D does not have any transitions, so we can leave it blank. G, G, G has one transition, which takes us to C. And when we do the E closure, so even if we do the E closure for BD, it's still going to be the same. So when we do the E closure for G, it's just going to be G because it does not have any transitions. It's going to be G, and for those of you curious, it's going to be just D. It's going to be just B. And but you can just leave it. You know, I can just write it. So this has a transition for C, which takes us to H. Takes us to H, and we're going to name this 8. And now that we have the 8 over here, we're just going to say for transition G, we're just going to put an 8. Yeah. Now, where do we have next? So we're going to have L. L, we do the E closure for L, it's just going to be L. It takes us nowhere else. Where? Then we have H, do closure for H, takes us nowhere. And I think that's it. I think that is the that is the transition for, at least that's how we generate the SLL, the table for the SLL pause table for from an NFA. At least this would be our DFA over here. If you draw it out, you'll get that. But in this case, we don't have to draw out the DFA. What matters is the transition table. So this is a transition table. And it's also our pause table as well. So build a cross-reference pause table. Add shift actions for transactions on terminals and go actions for transactions on non-terminals. So now that we've built that cross-index table, we're going to add the shifts and go actions. So it's quite simple. We're going to add the shifts here on the green bits because these are the terminals, as the instructions say, for terminals and the go actions. So the way this works is that you can just, at the beginning of each stage, we're gonna say shift. But you don't have to write down the full work. You can just write down S as well. So for all the green bits, so we're just gonna do this, S, 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 and S as well. And then that's everything. And for all the gray bits, which are the non-terminals, we're gonna put in the go. So here you can just write down go to 4 or just G4 and just G4 and just G4, G5 and G5 and G7. So yeah, those are the first actions. The other actions is we're missing 2 actions. That is the reduce action and accept action over here. I'll just put in a reference for that. Let's see, using as a constructor. Here, there you go. So, so these are the actions. Okay, here we go. So we've got the shift action and the go action. So now we're missing the reduce action and the accept action. So to add the reduce action, we have to calculate the follow. So calculate the follow for each non-terminal. And for this purpose, we add one more rule. S prime prime for S prime dollar sign. So it's just an additional rule on top of this one. And I'm just going to copy this, put it over here. Since the first rule is this, means the second rule is T prime prime produces T prime dollar sign. This is just the reason we're adding this extra rule is just for because we're doing the follow set and we want to handle the end of the file or end of the line conditions as well. So to get the follow set, we first generate the first set. So you already know how we do this, so I'll probably just speed forward for this one. Yeah, it might take a redonkulous amount, an unnecessary amount of time, but this is, let me see if I can yield over it. See, so T prime, uh, T prime prime, the follow of T prime prime is just going to be empty. So the follow of T prime is going to be the first of dollar sign, which equals to the dollar sign, nice. And then you have the follow of T, which equals to follow of T, which equals to the follow of T prime, union or subset. See, the first of C. So this would just be now the first of T prime would just be dollar sign, so it's just going to be that, and the follow of R is just going to equal to the follow of T, which we already calculated here. This then, and yeah, this means nothing. That means nothing. And yeah, that is it. So that's the follow set for this. And now that we've added this over here, we're gonna go through the table and we're gonna make use of those numbers. So these numbers over here now come into use as well. And these will help us put where reduce P, where P is a reduction number. P is the production number. And we're going to add those reduce to that production number in here. And the way to do it is that wherever this, like wherever B is contained, we're going to add reduce 0 in the follow sets over here. So here's an example. Oh, did I forget to put in a dollar sign? I think I forgot to put in a dollar sign. So I'm forgetting an extra column here. Here. Just undo. Yeah, I forget the extra column here. For dollar sign. There you go. Okay, so yeah, I forgot to add that. I forgot to add that. So the way this is going to work is let's see B. Which sets contain B? The final state B. So okay, let me just move it so that we don't have to scroll up and down so much. I'll just put this over here, and then put this over here, and then we have put this follow set over here, and put this over here. I don't think we need that anymore, but hey, I'll just keep it there, just for bookkeeping. And now I'm gonna need the pen tool. All right, so which production rule has B? So this one has B in it, and none other has B. I don't see a B here. Okay, cool. So since this has B, we're going to add reduce 0 or R0, in which column we're going to add it in. So which production rule is this one? It's for T prime. So T prime only has this in its follow set. So we're going to add it over here. So we're going to add our reduce 0 over here. So I'll just type it in. Let's put in, okay, add these again. Okay, so we're gonna put this reduce 0. Awesome. And now we got that. Switch to pen tool. Oopsie. So switch to the pen tool. So now I have D, so where we can add reduce 1. So this was reduce 0, this one is reduce 2, this one is reduce. Will tell us where to put the reduces, right? So to put reduce 1, because this is production number 1, where is D? So D is over here, and is D anywhere else? No, it is not. So this set contains D. That means we have to add reduce to where. So what production rules? So this is for production rule T. So we're going to look at this T over here, and we're going to add it in these columns. So for this over here, we're going to add it in C and the $sign over here. So I just remove all of that. Y. Reduce 4, erase. There you go. Much easier. So this is going to be where we put reduce 1. So you can also just write reduce 1 or just R1. All right. So now we have reduce 2 where H is, and H is only here and nowhere else. And H, what production rule is H? It's T as well. So that means we're going to add it in column T. So yeah, R1. And we're going to add R1 over here. So H is going to have R1, and here it's going to be R1. Cool. So now we're going to have R3, which is I, and it's going to be that. So which rules have I in them? So this rule has an I, this rule has an I. No other rules has an I, so it's just these two rules. And we're going to add it in C and $sign. So C and $sign, so we're just going to add reduce 3 into C and $sign. Reduce 3, reduce 3, reduce 3, reduce 3. There you go. And now reduce 4. We're going to add that into L. So L appears here. Let me just get an eraser. So L appears over here, and I don't think it appears elsewhere. Yep. So erase. So here we're just going to add reduce 4 and reduce 4. And now we've added our reduce. So reduce with the production rules. Yeah, now our table has our reduce over here. And the way reduces work is that the idea is that since SLR is bottom up, meaning that it starts from the bottom of your tree and then the tree gets built in from top to bottom, from bottom to top. The reduce means that we're reducing this element to this element into this production over here, right? So now that begs the question, how do we know if we're building from the bottom up, how do we know if we've reached the top? So you know you've reached the top if you reduce to rule number 0, because at the top you'll have production rule 0 over here, where it's T prime produces T, and this is production rule 0. So this is how we know once we reduce from T to T prime, we know that we've completed the tree because now we're at the top and we don't have to continue anymore. And that's what the accepts action is. Pausing has completed successfully, and this happens if you reduce to 0. So to add our accept, we just go to our table, and where we reduce to 0, we just replace it with except, or you can just write ACC or just A. I prefer to write ACC. And anywhere else that has reduced 0. And that is your pause table over here. And let me see if we're missing anything else. So for this purpose, we add one more production rule. This, when a DFA state contains an accepting NFA state marked with the production rule number A, where non-terminal is for P is N, find the symbols in follow of N and add a reduce for P. Action in the DFA state, whole thing. If pause, if production P is the production added in step 1, and accept state action instead of reduce P action. So we've already done this. So we replaced reduce 0 with accept, and now we have our table over here, our SLR pause table. And how do you use this table? You just apply this algorithm over here. So you'll be given like the same input over here. You'll be given the same output over here, and you just use this algorithm to generate the thing. So it just turns into an algorithm problem, and you can write it programmatically like so. There you go. No, this is for pausing. I guess there's no programmatic way of writing this. All right, so there's no programmatic way, but there's no programmatic example in the textbook on how to write this, but it is possible. You just need this table and you just follow along the transition, and yeah, eventually you do that. So that is how we do uh, pausing for SLR and LN1. Hopefully this helped. This give you a better idea of how to do things and how to handle it. It's not too difficult. Just follow along and you should be good. Thank you very much.